Okay, so the point of my talk today is to introduce the topic of proof by reflection and sort of give the bare essence of what it is. I'm going to go ahead and preface this with, I read a tutorial on this about a semester ago, and this is more or less a regurgitation of that tutorial. It was by Gregory Melika, and it's only like the first third of the tutorial, so if you like this topic, I encourage you to check out the rest. So a good way to start to understand what a proof by reflection is to start to understand the problem that it's actually trying to solve. So we're going to run some code that runs into this example. So this is an inductive data type. The inductive data type basically says that if you want to prove that a number is even, well, you can start with 0 and prove that and just instantly get that that's 0 by the even 0 rule. And then if you want to prove that a number is 0, you can show that some number which is 2 less than that number is even, and then you can learn that that number is also even. So that's what those two rules are. So we can do some proofs with this. And hopefully that's still pretty legible, though I don't have, it's going to keep juggling these around as I step through this proof, but I'll try to keep them in order. Okay, so for instance, to prove that 0 is even, we just need to apply the even 0 rule. To prove that 4 is even, we need to apply the even successor rule, and then that gives us the goal that we need to show that 2 is even, which if we apply the even successor rule, that shows that we need to show that even of 0 is even, and we have that by the base case. Okay, so I don't know if any of you have ever seen an Adam Chapala talk, but he loves to create tactics that do everything. I'm just going to wrap these two different sort of constructors that we can apply to build proofs of evenness together. So to prove that any number is even, we're first just going to try to apply the even successor rule until it can't be applied anymore, and then we're going to apply the even 0 rule. So this scales up to quite large numbers, but we'll see that it starts to slow down rather quickly. So here we're proving that, here we're building a proof that even of 4,096 is even. And we just got done, and you can't read the time because it's on this, which is still really small. But that command that I put in for it shows that it took 5 seconds roughly to build that proof. And then we can step past the QED rule, maybe. There we go. And QED here is saying, okay, you built a proof, now we have to check that that proof actually meets the specifications of our language. And it turns out that the proof that we built is actually fairly large and takes a little bit of time to check.
Is this linear time, or is it worse?
So this one is, well, actually I don't know that to be certain. It does seem to be about linear, just from...
I don't do it now.
Okay. So it scales, I will say this, it scales much less well than Haskell's type checker does. I was going to be like, maybe we shouldn't pick on Coq that much. I mean, here's how long Haskell does, and Haskell just instantly does this. But it's also not doing the dependent reasoning and other things. So, but I would like to say that at least Coq here is trying to minimize the number of bugs, so they're probably not optimizing for performance in this particular case. I was going to print these out and show them to you, but this, I don't know if I can get that window big enough to show any of the text there. So I think I'm going to punt on that part due to resolution issues. Yeah, I'm going to give up on that part. Okay, so it turns out that these are really big proofs. Later on, there's like a sort of visual distinction. Oh, yeah, so you can see that it's actually just a chain of even S's is what the proof is going to be. And there's going to be 2,048 of those to show that 4,096 is that. Okay, so what can we do to solve this problem? Well, one thing we can do is we can make building the proof faster. One way we can do it is we can use, so the language of tactics, LTAC, is a dynamic programming language. We can use a static programming language to build our proofs. So here is Galena. It's the term language of Coq, actually, which means that it's the language that Coq reasons about as a logic. But we can write our build even in this, and it's going to be a partial function because not all numbers are even. So we use sort of a maybe monad sort of approach to that. And then we wrap a tactic around it that extracts it or fails if it doesn't work. And you don't really need to worry about the details too much, except for the fact that like we're calling eval essentially. We're in like a meta-programming language, and we're just calling eval on a Galena term. And so we now have this tactic where if we time it and we prove even, it goes a little bit faster. Cool, but it still takes a long time to type check this term because we're building the exact same term. So let's make type checking faster. Unfortunately, I'm not going to hack on the Coq kernel today. So instead, we're going to try proof by reflection, which improves type checking time by minimizing the size of the term that you produce. And how are we doing this? So the idea is that we're going to essentially carry as much of the computation as we can over into the world of Booleans, and we're going to write a Galena program that calculates some Boolean check on a value, and then we're going to reflect that back into the logic that we're working with. So let's see what that looks like in like a very abstract sense, and then we can see what it looks like in a concrete sense. So for a property P that we want to prove, we define a predicate P question mark in this case. And I'm going to check the time to see how I'm doing. I never started the timer, so we're just going to say I'm doing well. Okay, yeah, we're doing well. So we're going to define a predicate P question mark that checks if P holds. And so this is a Galena function, P question mark. And then to show, then we show the soundness of P. That is, like, if P is equal to true, P of X holds. We just do a proof of that. And then for proving a particular, or P for a particular X amounts to just type checking the expression. Well, is equality sound? Like if we pass in an equality proof at the right type, is it sound? And one thing to note here is that this P question mark is actually like a type. So the type checker actually runs this check and makes sure that it unifies. And if it doesn't, you just get this like lame error message that's like, P of X is not equal to P of X, or something like that. No, P of X is not equal to P of true. Sorry, P of X is equal to P of X is not equal to P of X equals to true, is the exact error message that you'll get. Okay, so let's ground out to some reality here. So we write is even, which is our decision procedure. It just is basically the 311 style, and I'm going to catch our proof back up here. It's just the 311 style evenness check that you would expect. We write a proof by induction that is even is sound. So I say by induction, but Coq is kind of lame and doesn't like it when you skip constructors or like downgrade by 2. So this is a hack to get around that slightly, which just gives us a nicer induction rule. So our base case, I'm going to make this window a little bit bigger. Our like false contradiction case 1 is not true. And then our inductive hypothesis, where we have to apply it. So we apply one level of even, and this is actually like where whenever we apply this, this is where like a term is getting built up. So we apply one level of even successor, and then we apply the recursive call essentially. And then the argument to that I just proved by assumption, which is in the context there. Cool. And then a proof by reflection is just applying the soundness principle and then solving the reflexive case, which we can do there. And that goes through rather quickly, is the good news. Like, really fast. And if we print it out, you can actually see that the term, instead of being a big stack of ones or a big stack of successors, is just this is even sound and then EQ ruffle. What'd you get?
That's really cool, but I feel like I missed the trick here that made that happen. Like, was there some point in that code that was the reflection part?
So I would say that those two steps, defining a predicate and applying its soundness principle, is the proof by reflection. It's like the step where, I mean, there's like, you can't apply the soundness principle, the soundness property, without defining the checker first and proving it sound. But like applying the soundness property of the checker, that checker reflects. The Boolean like checker reflects the property P, is like proof by reflection, is what I would say.
So, unlike in the previous approach, with this one, don't have access to some chain of data constructor application.
But you do.
Oh, okay.
So it's just the type checker doesn't have to type check it, because you like type check this thing that said it was sound to do this, and then you just applied the term. So that term does get built while type checking, but the term itself is like sound by construction. So like you don't ever have to type check the big long chain. You just have to reduce it.
Okay.
Is my understanding of it.
Kind of floating somewhere.
Yeah. And I'll actually show that to you in a sec. So one might worry, in fact, that's the very next line. One might worry that this proof is not actually equivalent to the other proof. So if we go back to the top of this file and mess something up so it rewinds, and then do a find and replace of QED, which is like the standard proof technique for hiding all the proofs, for define, which is essentially what functions use in their definitions, so that all the computational content is still present. And we just go through and replace all those real quick. And then I have to remember, I think it's that. Nope. Okay. I'm just going to have to drop this buffer all the way down. Okay. Boom. Here's where we want to be. Okay. So if we get it all the way down, then I actually, like this proof just says that the proof by reflection is actually the same proof term as the other one. And essentially this reflexivity forces it to unwind and check that they're both the same. And we'll get there after all the proofs by not reflection go through.
While it's getting done, can I ask something?
Sure.
So if you go back, it's done.
Well, the reflexivity actually has to type check both those terms then, or whatever. If I go back to what?
So the soundness.
Okay.
So you say that P question mark X equals to true implies.
Sorry, this one right here, or are you talking about the?
Even here, like, so in theorem is even sign, you say for all n is even n equals to true implies even n. Why do you have to say true implies there?
So
It's the equation.
essentially you want is even, which is a Boolean equation, not in prop.
And what's your even n?
Even n was the type at the top.
Even n is the proof, like that n is even.
So it's not true implies that, it's the equality implies.
You're reading the parentheses. Yeah.
Yeah, sorry, yeah. There's a
Yeah.
That's a very good point. Sorry, not everyone's used to speaking. So it's essentially saying this even could return false, in which case you couldn't apply this. Cool. So that's all I got. Thank you very much.
Quick questions?
Nice.
Okay.
So if I had to summarize what a proof by reflection is, it's an optimization of compressing your proofs. Just to summarize that in one sentence.